And all these slides are on the webpage in the usual place for the course.
Yeah. Oh.
Apple Plus.
Good.
And you could drag it also to the side a little. Yeah.
Okay, so I'm going to talk about numerical optimization. So I guess you guys, William talked to you about root finding on Monday, I believe, right?
Mm-hmm.
So this is kind of a similar problem. The algorithms tend to be similar to some extent. And one way they're related is that if we can find this, if you have a zero, then certainly that minimizes the absolute value of the function. So that's pretty neat. And in fact, so that's one way which that's not a very good way to find a zero, but you can use that observation to make some algorithms in general dimension better to find zeros. But I'm going to talk about optimization and in general dimension. So the first thing to note is that essentially minimizing in one dimension is pretty easy. There's lots of different ways, but there's a simple algorithm that's similar to the bracketing algorithm for finding roots, which you talked about that, I believe.
Mm-hmm.
And basically, the only difference is you have to realize that to bracket a minimum, you need 3 points, because to bracket a minimum, you need 2 points that are bigger than, you need your approximate minimum and 2 points around it that are bigger than it. So, and so then the way the algorithm basically works is you start out with a sort of potential bracket, and then you pick a point in between, say, B and C. And then, so suppose I pick this point. Then if this point is bigger than my minimum, I replace C by B. Now suppose I choose another point in the interval. Well, if this point is less than what was my minimum, I make my bracket now this point, and this point. So you can keep doing this by just evaluating points in between and tweaking your bracket, and you can sort of create a pretty naive algorithm, but that works. And in one dimension, it doesn't necessarily, the dimension is one, there are better ways to do this using derivatives, but in one dimension, the speed isn't particularly, one dimension is easy, essentially. The problems are, usually the problem is if you have higher dimension, that's where you want to be more clever. So the point is, in one dimension, there's not that much that's interesting, so I'm not going to say much about it other than to indicate that there are ways. Does that kind of make sense, that general way of searching for a minimum? Question about that? I'm not really going to use it at all, I'm just pointing out that there are ways. So the problem that we actually want to talk about is, suppose I have a function from Rn to R, and I want to find a minimum. And you could replace minimum by maximum, but it's equivalent because you just multiply the function, take the negative of the function, and you flip it around. So let's just talk about minimums. And hopefully hopefully this minimum I'm trying to find actually exists, but let's assume there is one. Otherwise, the algorithm won't work, so that'll tell us that. And we're also going to assume the function is smooth. If the function is not smooth, then things are a little bit harder. There are algorithms that don't use any smoothness, but they don't converge as fast. So let's assume it's smooth just for simplicity. And so recall from vector calculus or whatever, the gradient of the function is just the partial derivatives in all the directions, and that's a vector. And the important thing about this is that at a minimum, the gradient vanishes, also at a maximum. The reason is just because essentially just from one-dimensional calculus, you know at a minimum in one dimension your derivatives vanish, and this says that in every direction the derivatives vanish, so you have to be at a minimum. That's basically the idea. And the other important thing about the gradient is that in addition to when it vanishes we have a minimum, it also, if we're not at a minimum, it points in the direction where f is decreasing most rapidly. So you probably, let's take a little plot so that you can see what I'm saying. So here's just some random function I picked. Here's some random function I picked. And then if I go here and plot the, so what I've done here is I've plotted the function and I've also plotted the gradient. So this is the gradient and I've plotted it as a vector field. And you can see that, that the gradient is, if you look back up at the original graph, that if you sort of imagine projecting this 3D picture down onto this 2D one, you can see that the gradient is pointing down at each, it's always pointing towards where the function is going, the direction to go to get to a lower value. And another thing that's important is that you can see from this picture, the gradient is actually orthogonal to the level sets of the function. Let's see this. So from this observation, you can see that one naive, but basically it's the way you do it is you say, well, if I start over a point here and it's not a minimum, you don't know what the whole function looks like because you can't just, I mean, you could just graph it if it was 2 dimensions, but you know, if your function is a function of 10 variables, then you can't just graph it and see what's going on. But what you could do is you could compute the gradient, and it's going to tell you a direction to go in order to get to a place where the function is smaller, at least locally. And so one could hope that if you just sort of compute the gradient, find a direction, step that way a little bit, compute the gradient again, find a new direction, step that little way, keep doing that, then you'd end up at the minimum. And basically that's the idea. So to find a minimum, what we're going to do is we're going to pick a point, compute the gradient, step that way, compute the gradient away, and take another step, and we're going to keep doing this until the gradient vanishes. And now this is very naive, and there's lots of things that can go wrong. I mean, that can go wrong with this. So the most common problem with this sort of thing is illustrated by this picture, and it's the problem you can have if you have a very long, narrow valley. Remember that the gradient is always orthogonal to the level sets. So if you have a very long, narrow valley, what's going to happen is you're going to go bouncing back and forth. You're going to take little steps and sort of zigzagging. And you'll sort of get there, but the problem is you're going to have to take a lot of steps. So the algorithm will take a very long time to converge. And that's basically the main sort of problem is, the algorithm, you want it to actually finish in a reasonable amount of time, and so this sort of thing can create problems. So, so basically...
Josh, have you said what the step size is?
No, so yeah, so so basically there are, basically the details in making this algorithm better are the things that you want to do is choose how large of a step you want to take. One way of doing that is you could say, well, I can choose my direction and I can minimize the function. I could sort of, if I just pick a direction, I can look along that function just along that line. And I can use the one-dimensional minimizing algorithm I have. And so I'll go all the way out to a minimum, and then instead of just stepping a finite size, you can try and go in the direction until you find a minimum just in that direction. So basically the idea here is you would, does that sort of make sense what I'm saying? You sort of go in your direction until you found a minimum, because that's just reduced it to a one-dimensional problem, which we indicated is kind of easy to solve. Once you found a minimum in one direction, you compute the gradient again, look in that direction for a minimum, and keep going. And that's one way of doing it. That's a better algorithm. There's also other things you can try and do, which is instead of maybe exactly going orthogonal to it, maybe you want to go, as long as you sort of go sort of in the direction of the gradient, it'll be decreasing. But you might think that maybe I can choose a slightly better direction, so if I minimize along that line, and then I sort of compute the gradient again, I can sort of get there in fewer steps. And there are these, they're called conjugate gradient algorithms that let you sort of choose better directions to sort of try and do this in fewer steps. I'm not going to talk about those because they're much more difficult to sort of intuitively understand. They're a little bit more difficult to describe, but there are algorithms that basically involve choosing better steps, and that's the idea. Does this general idea though make sense? Right, and the other thing that you have to figure out is when do you stop? So basically you want to stop when the gradient's 0, of course. The gradient is never going to be 0 because we're doing this numerically, so you kind of have to figure out what is a reasonable tolerance to determine, and that's a little bit more subtle in some cases. But that usually uses the second derivatives. Is usually you use the Hessian matrix to sort of help you figure out when to stop. Does that make sense? So there's a lot of subtleties in sort of exactly how you implement this, but the basic idea you can see is pretty simple. And for simple problems, the basic idea will work fine, and for complicated ones, or sort of for functions that are well-behaved, the basic idea will work fine, and for functions that are not well-behaved, sometimes even really good algorithms won't work. So that's kind of it. And I'll give some examples of a poorly behaved function. Well, that didn't work very well. So, I just want to sort of talk about one reason you might want to minimize a function, or why you might want to minimize a function of a lot of variables. I mean, so the one application that I've seen it come up in most frequently is in statistics, and I'll describe why. So please ask questions if something's not clear, because this part in particular is kind of abstract. So I want to be able to clarify if it's not clear. So the idea is, suppose you're doing some experiment and you measure some values. So you're measuring height of plants or something under different treatments of chemicals or something like that. And you want to try and construct a model for how different factors influence your experiment. And so you believe that there's a function p which depends on x and then n other variables, which I called a. So you believe that there's some set of parameters so that p of x, when a or the a's are set to those parameters, gives you the probability of measuring x. So you want to determine what are those parameters. And so remember that if you have two independent events, the probability of them both happening is the product of the individual probabilities. So that if I measure x1 and x2, and I have those parameters right, the probability of measuring both of those things is going to be the product. And in particular, so now I have n, or actually, so that should be an m. I have m measurements, and that should be the probability of getting those m particular measurements should be the product of all of the x's plugged in multiplied together. That kind of makes sense. Now, the idea is that since I actually measured those values, the probability of obtaining those values should be somewhat higher than some random set of values, because they actually occurred. So what you hope is that if you can maximize this probability, then if you can find, so now remember the x's are fixed because we've measured them, the a's are the variables. We want to maximize those a's, and we want to hope that that gives us an estimate of those parameters. And usually what you do is you take the log of this because it converts it to a sum, but then you want to multiply it, and then you multiply it by a minus sign, so that, because the function is less than 1 because it's a probability, so the log is negative. And then you take a minus sign, so that gives you a minimum problem, because I've switched the sign. So we want to minimize this function. So that's the idea of a problem where this might occur. Let me do an example, and then I'll make sure that the idea of why we're doing this is kind of clear. So I'm going to do the simplest example of such a thing. Right, and of course, if we have a bunch of data, if we have 1,000 measurements, then each function evaluation is going to require, evaluating that sum is going to require quite a lot of floating point operations, so that could be expensive. So here's an example, so a simple example. So this is the standard normal distribution, which you may have seen, where mu is the mean and sigma is the standard deviation. And I've plotted it down here in case you forget what it looks like. And so I'm going to do this procedure I talked about. So I'm going to take just the numbers from 1 to 100, or actually 0 to 99. And I've created a function which is the log of that. And what I've done here is I've summed what happens when you substitute all those data points into my function. So I didn't evaluate this thing. Right. So maybe just, well, I don't know if I want to print this out. Let me make this smaller just for a moment. So if this was just 10, you guys can see what I did. Reevaluate. So you can see that what is this sum? It's the sum of this function evaluated with, 99, 98, 97, 90. I plugged in all my data points into the function, and I've summed up the log of that function. So it's kind of. So I'll talk about the minimize function, but specifically, but I just want to sort of illustrate now. Let me make this bigger. So you can see that if you do this procedure I found out, this minimization procedure estimated that mu was 49.5 and sigma was this. And if you think about computing the mean of this, that's exactly what the mean of that list of numbers is. And that's exactly because the mean and standard deviation that you are familiar with exactly arises by assuming that your data is normally distributed and doing this procedure. But the thing is, for that function, you can analytically compute what the minimum is just by taking the derivatives, if you think about it. And that function is simple enough that when you take it's an exponential, so when you take the log, it just becomes linear, and you can just analytically get the standard formula for the mean and the standard deviation, which is what you of course normally do, but this is really what's going on in the background.
Could you do it with 100 random values between 0 and 99 instead?
I could do that, we'll see where it is.
Right. Nice.
So I did that. So this is really what you really are doing. Of course, I mean, it's much easier to do it when you have a very simple probability distribution. But in general, there are cases where you want to fit data to something which isn't normal. And how do you estimate the parameters that you might not be able to just analytically solve this maximization problem, and you're forced to resort to doing this numerically. And this happens a lot in statistics, in sort of more advanced statistics, where you want to model data by more complicated distributions. And I'll do an example of this in just a moment. But I just want to see if this, because I know this is kind of an abstract and sort of a random deviation to statistics, to see if anybody has any questions about this. Or anything that I've said so far. Okay, so, and actually, one other thing I want to point out is you'll notice that the standard deviations don't agree as well as the means. And the reason is, if you think back to the formula for standard deviation, there's this 1 over n plus 1 that people use instead of 1 over n that always is confusing, and no one ever explains why it is, other than that it's supposed to be better. And the reason is that this estimate it's this unbiased versus this estimator. So this estimate is not unbiased, but it's what's called a maximum likelihood estimator. So when n is very large, of course the difference will be sort of nothing, but that's why you're getting that small difference, and that's where that difference arises. So if you do it this way, you would get the 1 over n that you expected. And of course, and this is just a contour plot of the function we were minimizing, and that was for the original data. So now I'm going to do a different example. I'm going to do the same thing with a different example. So now I'm going to assume that my distribution looks like that. And that function is kind of weird, but you can see that it looks very similar to the normal distribution. And the parameters a and b are kind of similar to the mu and sigma. If you change if I change b, I can shift it over. So it's kind of like where it's centered and how peaked it is. And the difference is that this distribution lets extreme events have higher probabilities, so it has bigger tails. So the normal distribution, very sort of extreme events are less likely than here. So maybe we think that this is a better model for our data than the normal distribution. So, so I've loaded, so A is a big array with a bunch of numbers, and I've loaded the data in. And so just to illustrate the algorithms, I want to write a very simple gradient descent algorithm, and I want to show how that works. So, so we know we're going to take the sum of the logs, so I've actually set here p is equal to the log of that function. And we're going to explicitly do this, so we're going to need to compute the derivatives. So I've computed the derivatives. And over here, have you talked about the fast float thing? So I've made the fast versions of them. And then, so the function I'm actually going to minimize, remember, is I'm going to plug all the data points in A into my function and sum up their logs. So this pfunc is going to be the function we're actually going to minimize, and its gradient, you just sum up the gradients for the original distribution. And so that's what's going on there. That's what that function does. So now here's my very naive, this is completely naive, but hopefully it'll get the idea, a very naive implementation of the algorithm that I described. So this point array thing is because I'm going to keep track of the points so I can plot later on which points you went to during the thing, so kind of ignore this for the moment. But the idea is, and n is the number of iterations. So we're going to iterate through, we're going to compute the gradient. We're going to, so I've created a function which I'm parameterizing the direction, I'm parameterizing the function along the line given by the gradient. So I'm just sort of moving in the direction of the gradient, so that becomes a function of one variable. What I do is this optimize.bracket uses that bracket algorithm I described to compute the minimum. And then I multiply that, wherever that minimum is, I multiply it by the gradient and add it to my original point. So I find the minimum in one direction, and I'm gonna set my new point to be the minimum that I found in that direction. And basically remember the gradient, the minimum is going to be where the gradient vanishes, so I'm going to compute the norm of the gradient vector, and if it's small enough, I'm going to stop. That's the idea. Yeah?
The scale factor alpha is fixed throughout the iteration. It doesn't change where you evaluate the gradient. You feed it into
the alpha is how big of an interval you're looking for the minimum in.
But you're multiplying it times the gradient, and the gradient's not normalized.
Right.
So it doesn't really determine.
Yeah, you're right. So a better way to do this is,
The gradient could be big someplace and small.
yeah. So that's the subtleties of the, yeah. This is a stupid way of doing this is the point, but it's sort of the simplest, naivest way of doing this. It's kind of the point. So now I just ran this, and you see it worked. So I just ran this. I started at this point, 1, 0. I said the maximum iteration I was going to allow was going to be 1,000, and I gave it the function, the gradient, and this was the tolerance. And if we now plot, you can see already that, so I stored the points that I went to in this array, so I'm going to be able to plot it. So, so now this shows you the sequence of points that I traversed during this. So you can see I started here, and as expected, I went orthogonal to this contour line, and I jumped over to here. And then the next thing is I again went orthogonal to this contour line, and I jumped here. And you can see we're doing this zigzag effect that I drew the picture of. So, and you can see that happening. And eventually I end up around there. And then, so let's plot the function for the values we found. So for the values we found, it looks like this. And actually, just for comparison, I used
OS 10.
Oh well. Well, anyway, you can see the picture there. I don't know why I can't move it in the. It must be the X11 not working with the projector. But what I did is I empirically found that I used R to compute the distribution, and you can see the scales are not correct, but it has the same feature that it's centered around 1. If you notice, a little less than 1, and you can see the width is the same. So R computed an empirical distribution that matches the thing we found through our optimization. Does that make sense what this thing is describing? And if you want to look at the function we just minimized, let me make this. So this is the function we minimized, and you can see that the minimum we found is somewhere in here. And you can see that it's, that's what the function looked like. And so this is this algorithm which I'll talk about, this thing that's just part of Sage that does all this automatically for you. You can see that it computes the minimum much faster because it uses a much less stupid algorithm, but it gets the same answer. So,
Could you do time it on that whole thing?
on this thing?
Yeah, time it, and then one word, time it. Or maybe, yeah. And then in double quotes, just give the rest of the line. I'm just curious how long it takes.
Do I have to give it as a function?
Yeah.
Oh, it's because it's, yeah.
I hope it doesn't do it 625 times. Okay. 313 milliseconds.
So,
Nice.
yeah, so it's pretty good. So here's so I want to give an example of a pretty simple function where things go, which creates problems even for good algorithms. So let me turn off this. So this function, the reason it's bad is because you can see it's very flat. And the reason that's bad is that if it's very flat, the gradient's going to get very small. And if the gradient gets sort of below the machine's sort of tolerance of error, then the algorithm just doesn't know where to go because the gradient's essentially vanished, but it can't figure out a new direction. So what's going to sort of happen is it's going to end up going down here, but it's going to get stuck, and it's not quite going to get to the minimum, and that's just kind of difficult to deal with. So as an example here, so you can see though that the minimum is not anywhere near the actual minimum, and let me sort of illustrate that. So I've plotted, and you can see that this point here is it's not quite really. I mean, it's close, but it's not quite at the. It hasn't quite reached the region it's supposed to be. The error tolerance is very poor, just because it gets very flat, and so that's a common problem with these. It's just a general problem. So that kind of is. So I'm going to talk a little bit now about this minimized function that I was using. Are there any questions about anything so far?
This is all local minimum.
Yes, this is all local, right. So of course, right, so something I didn't say, so obviously this is only finding local minima. Obviously you could find a local minimum and you wouldn't be at the global minimum. And finding global minimum is very hard. I mean, so right, there's a couple things I didn't mention. So first of all, in all of these algorithms, I had to give a starting point. And the starting point, usually if there's a bunch of local minima, which point you start from will determine which minimum you find. So one thing you can often try is starting the algorithm from different points. You might be able to find more minimum, or maybe actually find the global minimum if there is one, if you sort of start from the right point. But I don't know if there's there's not really any good way. If you really need the global minimum and there are lots of local minimum, there aren't really any general ways of solving that problem.
There are techniques, but I think they take a long time.
Yeah.
I think they're called genetic algorithms or something.
Yeah, so that's difficult. So, and you can kind of see why, because really, you can't just look at the function from a distance and say, oh, that's where it is if it's in 10 dimensions. So all you can do is work locally, and so you can imagine you're kind of like walking around the function with a flashlight. That's really kind of what these algorithms are doing, hoping to sort of stumble where you need to be. And that's the way it is. So this is the function I was using. It basically just wraps some stuff in SciPy, which I'll talk about in a little bit. So this minimized function, well, what can you provide? What does it need? You need to at least give it a function, and it can be a symbolic function, as I illustrated, or it can be a Python function. And if it's a Python function, it should take as its argument a tuple. But if it's a symbolic function, it can just be the symbolic function. You also need to give it a starting point. If it's a symbolic function, it'll compute the gradient for you automatically, and it'll compute the Hessian for you automatically, and it'll turn all of them into fast versions of themselves. So if it's a symbolic function, it does everything. Of course, the point is that you might have a function that isn't just like a calculus expression. It could be the result of some other computation that you're trying to minimize, and so you can't just give a closed form expression. So you might just have to give it as a function that does something else first before it gets an answer. And so the gradient is optional. As I said, there are algorithms that they're called the Simplex Algorithm is the main one that do this without using any derivative information. Basically, this bracketing algorithm, you can generalize that to n dimensions, but instead of sort of 3 point, you kind of work with simplices. to bracket the minimum and sort of picking new points. So anyway, so there's ways of doing that if you don't have the gradient. And the Hessian, if you have it though, it'll usually make it faster. And the Hessian is again optional. If you have that, it'll be better. And there's a couple algorithms that you can use. So as I said, for Python functions, the simplex one is used. There's a symbolic function, this BFGS, which is basically it's an algorithm. It's similar to the gradient descent I described, but it does things smarter than the way that we did it. And there's also the conjugate gradient and the Newton conjugate gradient, which, as I said, they work by trying to find better directions, so you can try to avoid getting stuck in valleys. And here's some examples. So let me do. And so here's actually the source code of it. The source code, as you can see, it's quite simple because all I'm doing is sort of packaging things up and sending them off to SciPy. And that's basically all that this function does. So, and SciPy incidentally uses minpack. The Fortran library minpack is what it ends up passing everything to. So. Right, so as an example, so here I have a Python function that's going to, I'm going to use minimize with a Python function. And you can see for the Python function, as I said, it should take a tuple of n components as its argument. And I've also computed the derivative, and I passed it the function, the starting point, the function that's the gradient, and I told it to use that algorithm. And that's kind of the way that works. So that's that function in general. Right. Of course, you can always use SciPy if you want to. Like if you import SciPy, I don't think Williams talked about SciPy much.
Say something about SciPy.
SciPy is very good. So
it's good, okay.
So here's a bunch of optimization algorithms that SciPy has. These are the ones basically that are used by the minimize function. You can use them directly. Basically, the syntax is more or less the same as for the minimize function, except for some of the names. They say f prime instead of gradient, and there's some more parameters that you can tweak in the SciPy functions. Which also anything you pass to minimize will be passed on. But there are things like for error tolerances that you can change, and for controlling how things are done. If you need a little bit more if your thing is just not working and you think that you can maybe sort of tweak it a little bit and get it to work, you can just directly use you might be able to directly get something out of the SciPy functions. One thing to be aware of, the main problem, so SciPy and NumPy, so when you can create NumPy arrays, they're basically like tuples, but they're basically like lists, but the main problem is that you want to make sure that you actually create floating point numbers. And so the way to do that is, so one way to do this is to use that explicit raw evaluation. Another thing you can do if you're doing a lot of stuff with NumPy and SciPy, which I tend to do, is, and you're not going to be doing sort of symbolic or other more, is to just turn off the, make sure that just turn real numbers into floats. So it'll basically make everything function just like Python would. And that a lot of times, so this function actually will get very upset if you pass it a list of initial points that are stage real numbers. But if you turn them into Python floats, it's happy. So if you're going to use SciPy directly, you have to be aware that it really wants Python integers and Python floats oftentimes. And if you give it stage integers or stage real numbers, it will not sort of behave well.
Does NumPy only work with C double float?
As opposed to,
As opposed to, like, for example, Sage has MPFR. Can I use that?
no.
You can use it, but it doesn't do anything interesting. It can generically work with any Python object.
So NumPy can contain, the NumPy arrays can contain arrays of arbitrary Python objects, but it doesn't store them. For doubles, it stores them as just a double star, which is efficient, and it can be passed directly to, but for general Python algorithms, it just stores a list of, it doesn't do anything smart.
So if I want to call the linear algebra package as part of NumPy, that expects doubles.
Yeah.
It has generic algorithms. It just doesn't do very much.
It's just, you're not going to, matrix multiplication using NumPy, if you have MPFRs, is not going to be any better than anything else in Sage. there's no really sort of fast way to, I mean,
He really cares because he has matrices with floating point entries where when he finds the eigenvalues as double precision numbers and then plugs them into polynomials, the rounding error kind of kills everything,
yeah.
right? So it would be nice. There, as far as I know, there does not exist a arbitrary precision numerical linear algebra library at all that's any good. Just nobody's ever written one.
Is it anything better than double?
There's a
the HEDAS stuff.
Yeah,
I don't know if it has.
the guy who wrote quad double apparently, as a research thing, made a quad double version of LawPack, I think, or BLOS.
parts of it. I think it was
Yeah.
on Lost, and I don't know if it was.
Yeah, I don't- maybe it was just BLOS.
Okay.
There are people who wanted to do this, but I don't think anyone's successfully done it yet.
Yeah, we'll talk about it. By the way, do you want to say anything about CVX opt? Since you're mentioning optimization so
Oh, yeah.
much, and
So,
that's another part of Sage.
So actually, let me say a few things. So first of all, if you want to, I really like SciPy actually. If you actually want to do numerical stuff, SciPy is really, really great, and I would recommend you look into it some more. So a good place to go is to go to the SciPy webpage, and they have some documentation under the documentation thing. And this tutorial, not the first one doesn't have much, but this second one, it's kind of outdated, but it has a bunch of, there's a lot of stuff. I think I have it
Jeez.
somewhere. Anyway,
Ah.
I'll open it up and you can see what it looks like.
This is a very nice tutorial.
There's also, so this is the SciPy tutorial. It's very good, and it has a lot of, it goes through a lot of different stuff, in not just optimization, but differential equations and sort of constructing meshes for finite element stuff if you want to do that or something. So that's a good one. There's also over here. There's somewhere. Where is? Oh yeah, so NumPy for MATLAB users. So if you know MATLAB and you're curious if NumPy can sort of do something, this gives sort of equivalencies between NumPy and MATLAB, and so that's very useful potentially. So there's a lot of stuff SciPy can do. It's really great. But as I said, the one thing to be aware of is if you're using SciPy in Sage, you have to be careful with that you give it the floats it wants and integers it wants, otherwise it'll complain. Right, so there's also, actually, so one other thing I want to mention that I'm not going to really say anything about it. There also is a function called minimize constrain, which does constrained minimization. So if you want to minimize a function, but you want to say, I want to minimize this function, but I want the first variable to only be in this interval. Or I want to minimize one function, but I want it to be in the region where this other function is positive. So that's a much harder problem, and there are algorithms, but they're generally not quite as, they're not as simple. But there is something that can do that in Sage, and if you are interested in that, you can look at that. There's also, as Wayne was saying, CVX opt. CVX opt is used in the linear program function, which is kind of like an optimization program. CVX opt isn't.
Hey, look, a bug.
What?
Gin itemize in the doc.
Yeah. Ooh.
And this be, you forgot to make it a raw string probably or something.
Huh, yeah.
Huh.
Well, okay, so a bug.
First bug today.
CVX opt is slightly harder to use from within Sage than MATLAB and NumPy is. It sort of has its own version of everything, and they're like matrices and stuff that aren't quite incompatible. So it's a little bit harder to use, but it does. The guy who wrote a very, there's Vandenberg, there's this book on convex optimization that's sort of a standard book that he wrote. He also wrote this convex optimization package. It can do a lot of stuff. I don't really have anything specific to say about it. It can do a lot of stuff. It does linear programming and plug-IO programming, and it might also be, it definitely could be interesting to look at if someone wants to do something like that. Yeah, so are there questions? I don't really have anything else to say.
Right, so we'll meet back on Friday. Come very ready to work on your projects. And if you want to coordinate working on anything right now, you still have a few minutes if you want. Otherwise, I'll see you on Friday.